Hello, welcome to Control Systems Lectures. In this lecture, we'll be looking at stability analysis. In control system, stability is one of the very important requirements. There are three main requirements in control system design. The first one, which we've already covered, is transient response, which specifies your rise time, your settling time, your percentage overshoot, and these must be specified as part of your specifications. And then the next most important thing is stability. A system must be stable before you can continue with your design or controller design. You can see, for example, a stable system will be this first figure here. If the ball is moved from its desired operating position, it will come back there. But if this ball moves away, it will hardly come back to operating condition. Same thing with this. So to give you an idea of what stability is when there are external disturbances, the system is able to come back or operate within the desired operating point. The next important thing in control system design requirement is steady state error. And this is the state of the system as time goes to infinity. And we'll be looking at this in subsequent lectures. The learning outcome for this lecture is the following you should be able to do at the end is to generate and interpret a Routh table to determine the stability of a system. To generate and interpret a Routh table in cases where either the first element of a row is 0 or an entire row is 0. You'll find these lectures from in chapter 6 of your textbook, Control Systems Engineering. Let's start with the definition of stability, and we are defining this for the linear time invariant systems. So stability is the result consists of the force response, which is your input, in this case CT forced, and then the natural frequency or the natural response of the system. So the steady state of a system consists of the force response, which is the input, and the natural response. And so a system is stable if the natural response approaches 0 as time approaches infinity. So in this illustration, you can see that in this system, as time goes to infinity, the system converges to its operating point. Same thing with this, as time goes to infinity, the system converges to its point. And you can also take note that the poles are located on the left side of the imaginary axis. Then a system is unstable if the natural response approaches infinity as time approaches infinity. In this case, you can see as time approaches infinity, the response seems to be increasing. Same thing here, the response seems to be increasing. So this is an unstable system. It will not converge to its operating point. And you can see that the poles of an unstable system are located to the right side of your imaginary axis. Then we have marginally stable system. So a system is marginally stable if the natural response neither decays nor grows but remains constant or oscillate. You can see that these two are remaining on the operating system. They are constant and it's not oscillating. Here it's also constant, it's not oscillating. But it means that this system being marginally stable, any disturbance could either make it to become unstable or it could be improved to become stable. So being marginally stable can be a very difficult situation. So these are a few examples to illustrate the stable and unstable system. And this system here is a stable system. And you can see that if you do the system analysis and you plot the poles and the zeros of the characteristic function of this system, you will find the poles will be on the left-hand side of the imaginary axis. And so this system is stable. As time goes to infinity, it converges to the desired operating point, which is in this case a unit step. And this is an unstable system. You can see here also that even though there is one pole that is on the right-hand side of the imaginary axis, we have two poles that are on the left-hand side, or that are on the right-hand side of the imaginary axis. So this system is unstable. As the time goes to infinity, you can see that the system is just increasing. So even though there is one pole on the left-hand side of the imaginary axis, this system is still unstable. So pole location for stability is what I've said, is the system is stable, is said to be stable if all the poles of the closed loop transfer function are on the left half plane of the S-plane. And the problem is, at times, this is not obvious from the closed loop transfer function. So the point we're trying to make here is, if you have a system closed loop transfer function, you cannot, by just looking at the closed loop transfer function, be able to tell if these poles are on the left-hand side or on the right-hand side or on the imaginary axis. So let's take, for example, so you have a system given in figure A, and you want to find the poles of this, and you want to find where the poles are located on the S-plane. So we do our transfer function, and then we are able to reduce this system to this transfer function. So this is the characteristic function which we need to plot on the poles. So if you look at this T of S, it is not very obvious that we know where the poles are located. For us to know where these poles are located, we need to factorize this, and this can be a very difficult task. So what we need to do is to find a way where we can tell from a system, from the transfer function, even though we have not factorized them into S plus A1, S plus A2, S plus A3, but that with this equation or this characteristic function, that we're able to tell where the poles are located on the S-plane. And that is where the Routh criterion comes into play. So let's do a little bit of historical interlude. Edward John Routh in 1876 proposed what became as the Routh-Hurwitz stability criterion. He's an English mathematician. And then in 1895, Adolf Hurwitz, who is a German mathematician, determined the Routh-Hurwitz stability criterion. And this stability criterion is what we're going to use in studying the stability of our control system. So what is the Routh-Hurwitz criterion? It is a method that allows us to determine how many poles are on the left half plane, the right half plane, and on the j omega axis, or the imaginary axis, without factorizing the characteristic function. So it does not give us the coordinate of the poles, but it does tells us how many poles are on the left-hand side, how many poles will be on the left or on the right-hand side, or even the ones on the imaginary axis. So there are two steps in using the Routh-Hurwitz criterion. The first step is to generate a data table called the Routh table, or what I love to call the Routh array. Then the next step is to interpret the Routh array that you've generated to tell how many closed loop system poles are on the left half plane of the S-axis, or on the right half plane, of the imaginary axis, or on the right half plane, and or on the imaginary axis. Note that this method could be used both as an analysis and as a design tool. So let's explain this. This is your closed loop transfer function. If you like, this is your T of S. And now you have your characteristic function, which is a subscript 4 s to the power 4 up to a0. So this is a fourth order system. The first step is you will then have s to the power 4 row, s to the power 3 row. So you will have 5 rows for s to the power 4 characteristic function. If the highest order is 5, you will have 6 rows. If the highest order is 3, you will have 4 rows. So you always have the number of the order of the system plus 1 rows. So in this case, we will have 5 rows. And then the way we arrange the coefficients of the characteristic function is we start with the s to the power 4 row, where you have, this is the s to the power 4 row, so you take the coefficient a subscript 4, and then you go to a subscript 2, so you skip the s to the power 3 row, and then you come to the last one. So you're basically taking the first coefficient, skip one, next coefficient, skip the next one, and another coefficient. So you keep skipping one coefficient and taking the following one, and then you formulate your first row. Then in doing the second row, you start with your a subscript 3, which is the s to the power 3. So you have a3, and then you skip one, and then you have a1, and then you skip one, and then this will be 0. So now you have formulated the two rows. The next is, how do you come up with the subsequent rows? So in order to get to the s to the power 3 row, what you do is you form a 2 by 2 matrix between the first column of your first two rows and the second column. So these two columns form these matrix. You take the determinant, which is the negative determinant, that's why we put a minus there, and then you divide it by a3. So what you're going to do is, along this whole row, all the determinants we're going to be formulating will be based on these two rows, and all will be divided by a3, a3, a3. So here is the first one. So you say a4, a1 minus a3, a2 divided by a3. Remember, you have your negative sign there, and that gives you b1. Then in order to get b2, you retain the first column of the matrix, and then you've already used this second column here, so you no longer use this. You take the next column and you form your 2 by 2 matrix. This again is a negative determinant that you want to find, so a0 times 0 minus a3 times a2 times a0 divided by a3, and that gives you your b2. You do the same thing with the next, which is b3. You still retain the first column, and you take the next, which will then be 0, 0, and that's where you will arrive at this next coefficient. Then you move down to a1 to s1 row. In order to get s1 row, you will now move one step down. So you no longer use your s to the power 4 row, but you use your s to the power 3 row and s to the power 2 rows to form your matrix. So here we have a3b1 as your first column, and you maintain this first column all through this row, and only the second column is changing. So in the first case, you have a3b1, and then you have a1 b2, and you have your 2 by 2 matrix. So you again divide this by b1, and again in this case you are dividing by b1, and all through this row you will divide by b1, and this gives you c1. The same thing you do here, keeping the first column, and you take the next one, which will now be 0, 0, and that gives you 0. And this is just to complete the matrix, and so this is going to be 0, and this whole row will be divided by C1. So that's how you form your Routh table. And now we'll use this example to illustrate. So the question here is that you are given this example and you are asked to generate the Routh table for the system shown in this figure and then interpret the result. So in order to do that, I would like to show you how by solving it for you. So the first thing we do is we find our transfer function, because we need to get our characteristic function. And for you to get your characteristic function, you have to reduce this into the simpler form, so into your input output. So in order to do that, we will find our TS. So our T of S for this system will be equals to, remember we said is G of S over 1 plus, so this is plus because here we have a negative feedback. If this is a positive feedback, this will be minus. If this is, since this is negative, this will be plus. Then plus G of S H of S. Now we know that this is a unity feedback system, so our H of S will be equals to 1. So this is equals to 1. And then this whole thing is our G of S. Okay, so now we need to substitute for G of S and for H of S into this equation and find our T of S, and the denominator would be our characteristic function. And then we can use the characteristic function in order to come up with our root array. So that's very important that you get your characteristic function. All right, so now so your T of S is equals to 1000 over S plus 2 S plus 3 S plus 5 whole thing over 1 plus 1000 over S plus 2 S plus 3 S plus 5. If you simplify this, you will get 1000 over S plus 2 S plus 3 S plus 5 plus 1000. So you can see that here, for us, even though this side is factorized, but we have a plus 1000 here, which means we cannot find out exactly the poles from this system. We need to incorporate, we need to open the bracket here and also put in our 1000. So this becomes, so our T of S is equals to, if you simplify it, you will get 1000 over S to the power 3 plus 10S square plus 31S plus 1030. So this will be your T of S. And now you can see that your characteristic function is this one now. This is your characteristic function. So it is this characteristic function that you will now use to create your root array. So we go to the next and say now we have formulated this and we have this and we need to create our root array. So we're going to have 4 rows because our highest order is s to the power 3. So let's do the Routh array. So you start with your, so we have s to the power 3, s to the power 2, s to the power 1, and s to the power 0. And then in formulating this, so you have s to the power 3, and the coefficient here is 1. We skip this, and then we have 31. We skip this, and we have 0. So what we're going to have is here we're going to have 1, 31, and then 0. And then for the s square, we have 10, then we skip this, and we have 10, 30. So we will have, and then the next will be 0, of course. So here we have we have 10, and then we have 10, 1030, and this will be 0. So the next thing we're going to do is to find the coefficient for the S1 row and the S0 row. And you can see that in S2 row, we can actually divide all through by 10. So what we can do is to say, divide this by 10, that gives you 1. Divide this by 10, that gives you 103. So now let's find the next row. And let me create a working space here. So what we have now is to formulate a matrix between these two columns. So this column and that column, which will be a 2 by 2 matrix. So here we have 1, 1, 31, 103. You take the determinant, negative determinant, and you divide it by this S2 first column, that is 1. So this will be divided by 1. So this will give us minus, this is 103 minus 31. And if you open this, this will give you 1 minus 103 plus 31, which is minus 72. So here we have 72 minus. And then to find the next coefficient here, we will have the determinant will be, we still keep the first column, that is 1, 1, and now the next column will be 0, 0. So this will be 0, 0, and then if you divide this by 1, this will definitely be 0. So here we have 0, and hence this will be 0. Then we come down here. Now we have to formulate our 2 by 2 matrix using these two immediate rows above the one we are trying to determine. So here we will have 1 minus 72. Okay, let me create some more space. All right, so we have the determinant will be, because it's minus determinant, so this will be 1 minus 72, and we'll formulate this with 103, and this will be 0. And we divide this by minus 72, and this will give us So if you do that, you'll be able to arrive, you will get, so this would be 0 minus 72 times 103. So we have, with this minus, this becomes plus 103 times 72. If we divide this by 72, since this is 0, this will, and then you have 103. So here we have 103, and this will definitely be 0. This will be 0. So this is how you formulate your Routh array or the Routh table. And the next thing is for you to be able to interpret this result. So it's quite easy in formulating the table. If you have any questions, you can always contact me. So now the interpretation of the Routh array. The Routh-Hurwitz criterion states that the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. So you know that our interest is to find out whether there are any poles to the right-hand side of the plane, because once there is any pole to the right-hand side of the imaginary axis, then the system is unstable. And so the Routh criterion is to help us to determine that. And the Routh criterion says that this is equals to the number of sign changes. So the sign like positive to negative is one change. So these are the things we now need to look at in the first column. So our attention must be drawn to the first column. If any pole is located on the right half of the S-plane, the system will be unstable. If there is a change in sign in the first column of the Routh array, the system is unstable. So now this is the Routh array we've just formulated. I just put it here nicely for us. If you look at, this is the first column we're looking at. And how many change of sign do we have here? We have 2 sign changes, and I will explain that. So you can see that there are 2 sign changes. That is, this is positive, then it became negative, then from negative it went back to positive. So these are 2 sign changes in the first column. And we're interested in only the first column. So this tells us that there are 2 poles on the right-hand side of the imaginary axis. Therefore, we can conclude that this system is unstable. I would like you to try the skill assessment exercise 6.1, which is in page 307 of your textbook, and see whether you can formulate the table. It is a 7-order system, which means you're going to have 8 rows. It will be a very good exercise to help you to master the application of the Routh-Hurwitz table. So this is the end of lecture 601. In the subsequent lectures, we're going to be looking at very peculiar cases. So thank you very much.